So as I said before, we still have a lot of work to do when it comes to integration, but I think we are ready to start talking more about applications of integration, and there are a ton of them. We won't get through all of them, but here's just an idea of some of the things that we can do. So we'll focus on more of the geometric things that you can do as applications of integration. We'll look a little bit at some of the science-based applications of integration, but this is just touching the surface. And so the first one we look at is area as it relates to integration, which you already have a idea of from when we defined integration in Calc 1. And so you know this idea that, okay, if I have a function, and that function is above the x-axis between two values on an interval, I can find this area by doing an integral. So let's say this is a, this is b, so it's the interval from a to b. This area can be calculated using the integral from a to b of f of x dx. Okay? You saw that through summations. You saw it through summations of rectangles in Calc 1. But one key was that the function was above the x-axis over this interval. Okay, so then a couple of things could happen, right? A couple of the things that could happen would be, what happens if the function's below the x-axis? What happens if my function is down here, and I'm still interval a to b, I'm still bounded by the x-axis, but I'm below the x-axis. And now my rectangles look like this, and they're all below. Well, the problem here is that the height of the rectangle is based off of the function value, and the function value is the y value. Well, the y value here is negative, so the height of this rectangle is defined by a negative value, and that's a problem because area can't be negative. So the area of this rectangle would be calculated as a negative, the area of this rectangle, the area of this rectangle, they'd all be calculated as negatives. We can't have that. So there was a correction that we need to make, and the simple correction was that we had to take the function and we had to multiply it by a negative. So to find the area, we would do the integral from a to b still. Then we do minus f of x dx. So we multiply the function by a negative. That would then take this value and make it positive. I mean, we could have also took the absolute value of f of x, but multiplying by a negative computationally is quite easier. And that little correction, though, that little correction would make all the difference in finding the area. If you didn't make that correction, the answer you would get would be a negative answer, and you can't have a negative answer for area. Okay, one more scenario. And this final scenario is that we have a function that's above the x-axis sometimes and below the x-axis sometimes. And we want to find the integral from a, say, to b. And so we want to find all this area here. Well, the problem is if this function, say f of x, is just integrated from a to b dx, we're not going to get the area. Because here we would add up these rectangles and we would get a bunch of positive answers. And without correction, we'd add up all these rectangles here, but the area of all these rectangles would be calculated with negative values because of the negative heights. And if we added all this together, some of this negative would cancel out with some of this positive, and we would never truly find the whole area. So what we had to do is we had to figure out, where is this location? We call it C. Where does it switch from above the x-axis to below the x-axis? And once we find that area, that spot, we can then take this piece and correct it, and then add it onto this piece. And so the way we would actually find the area here would be to do the integral from a to c of f of x dx. No correction needed, it's all above the x-axis, plus the integral from c to b of negative f of x dx. And so knowing how your function behaves with respect to the x-axis is extremely important when you're finding area back in Calc 1. What we're going to do here is not quite that. And it has some relationship to it, but not quite that, is we're going to try to find the area between curves. Not area bounded by the x-axis, where technically you could say the x-axis is a curve. You could say it's the line y equals 0. And that could show you how all this stuff is related. But what we're going to do is look at the area bounded between two curves. So say this picture right here. So I have one curve, say f of x. I have another curve, say g of x, and I want to find the area between those. So not bounded by the x-axis, but bounded between the two curves. So in here. And it's actually quite simple. In some ways, it's actually easier than all the stuff you had to do here. So, how are we going to do it? Well, we're going to look at two different areas. We know if f of x is here, we know how to find the area bounded by the x-axis and f of x. So this big area here, all the way down. And that area would be calculated using the integral from a to b of f of x dx. We also know how to find the area between g of x and the x-axis. Again, that's this area here. Here's g of x. Here's the area we're talking about, the smaller area. And that would be calculated using the integral from a to b of g of x dx. Okay, so now what? Now it's, how do I find the area that I wanted, which is really this area in between? Well, if I take this big area here, and I subtract out this piece in here, that should give me the area in between. So this integral minus this integral should give me what I want. And since the intervals are exactly the same intervals, and they're both with respect to x, what we could do is we can combine this into one integral between a and b of f of x minus g of x dx, and that's because of the sum and difference rule. Right, the sum and difference rule usually says we can integrate each one of these separately, but now we're going in that in reverse. We have these two separate integrals, we're putting them back together as one integral, and you get this answer. And so you see what happens is, if you just subtract the two functions, that will give you the area in between. Now that should make sense on a couple of levels. One, if you just think about two numbers, okay, on say a number line, and I have say 5 and I have 9, and I want to find the distance between them. Okay, what's this length? I would take 5 minus 9, and I would get 4. And I always want to make sure I take the bigger one minus the smaller one. Because if I did 5 minus 9, I would get negative 4, and I can't measure a distance in a negative value. Distance has to be measured as a positive, so I always do bigger minus smaller, but I would subtract them. Well, think about this right here. Let me clear this up a little bit. Let's think about this right here as the height of the rectangle, and that distance. Well, that distance is calculated by the y value here and the y value here, over and over and over again. Well, the y value here for all these is f of x, and the y value here for all these is g of x. So the height of these rectangles would have to be the bigger minus the smaller. So that's why we get f of x minus g of x. This represents the height of the rectangles, which is the same thing here in the single integral, right? In the single integral, f of x was the height of your rectangles. So that's one reason. Another reason why this should make sense is just the idea of how to find space. If you're looking at, something big and you take something out of it and you want to find what the remaining piece that's left, you would always, find the whole thing and subtract out what's missing. And that would give you the space that's left. And that's essentially what we did here. Now, notice the way these functions are oriented. F of x is above g of x at all times. So the y values for f of x are always bigger than the y values of g of x. That's important because the subtraction, the order is very, very clear. You have to go back to this. Also notice that both of these functions are above the x-axis. In this example they are, but honestly, it doesn't matter. We could change this up and we could still do the integral exactly the same way. And I'll show you a couple of examples. So let's say we have this scenario. Here is f of x. Here is g of x. Here is the x-axis, and I want to find the area between these two functions. So here's A, here's B. Now, they're both below the x-axis, but f of x is still above g of x for this entire interval. Okay? So what am I going to do? Well, what I can do is two things. I can find the area here, okay, bounded by the x-axis and g of x, so that's going to be my bigger area. And that area would be the integral from a to b of g of x dx, but because it's below the x-axis, I would have to subtract it, put a little negative in front of it. What I could also do is I could find this area in here, which is the area bounded by f of x in the x-axis. Okay, and that's the smaller area, which would have to be subtracted out. But that area would be calculated using the integral from a to b of negative f of x dx. Again, I have to multiply by negative because the function itself is below the x-axis. But then look at what we have here. We have a double negative. Well, if this negative comes out, it's going to turn all this into a plus. Okay? And if we then put these two integrals together, we would get the integral from a to b of negative g of x I don't know what's going on. Negative g of x plus f of x dx. Well, negative g of x plus f of x, isn't that the same thing as f of x minus g of x dx? And you still see, look, we're subtracting the functions, and we're still subtracting the top function minus the bottom function. Okay. I could give you one more scenario. I could say, all right, let's look at f of x being on top, g of x being on bottom. Here's g, here's f. One happens to be above the x-axis, one happens to be below the x-axis. Here's a to b, and I want to find this big area here. Well, same thing's going to happen, right? I could find this area. Oops, that deleted everything. I could find this area. I could find this area. And if I add those two areas together, that would give me the total area I'm looking for. Well, what would I get? I would get the integral from a to b of f of x dx, which would be the yellow one, plus the integral from a to b of negative g of x dx, which would be the red one. And if I add them together, again, the yellow plus the red should give me the blue, which is the total area between. Remember, x-axis happens to be in between. If I add them together, it should give me the total area. But since this is a negative, if I add the negative, isn't that the same thing as just plain old subtraction? And so I'm still f of x minus g of x. And so all that really matters is how these two functions relate to each other. The x-axis really plays no role. Are they below the x-axis? Are they above? Are they one below, one above? You no longer worry about the x-axis anymore. You worry about the relationship of the two functions themselves. And so if we have two functions that are continuous on a to b, and that's still important, the functions have to be continuous on this interval, because that's part of the fundamental theorem of calculus, is in order to be able to do definite integrals, your function has to be continuous over the entire interval. We'll talk about what happens if they aren't later in the semester, but for right now they have to be continuous. And g of x has to be less than or equal to f of x, okay, on the entire interval, which means f of x has to be completely above g of x over this entire interval. Okay. Then the area of the region bounded by the graphs of f and g, and the vertical lines x equals a and x equals b, is calculated by the integral by simply subtracting the two functions. So this is how we're going to find the area between two curves, but understanding how two functions relate to one another is extremely important. So knowing what the graphs of the functions look like is going to be very important. Now, sometimes you have graphing calculators available to you. You have graphing applications online you could use, but sometimes you don't have any of that. We can still get around doing these problems without having, stellar looking graphs. As long as we know the relationship between the functions, we can still get through this. So here's a fairly simple example. Find the area of the region bounded by the graphs of y equals x squared plus 2, y equals negative x equals 0, and x equals 1. Now, these should all be very easy for you to draw without using a graphing calculator, without using some computer graphing system that you found online. These should be very easy to draw. So if we were to look at this, obviously everyone should know y equals x squared plus 2 would be a parabola with its vertex at 2 on the y-axis. Y equals negative x is this line right here with a slope of negative 1 going through 0, 0 as the origin. And then here would be x equals 0 would be the y-axis, and here would be x equals 1. So that space that we're trying to find the area of is sitting right here. And so what we see here is this is the top function, let's say f. This is the bottom function, let's say g. And here's the interval from a to b. So based off of everything that we've discussed, the area should be found by doing the integral from 0 to 1. That's the width here. So the width goes from 0 to 1. And then the height component of this is the difference between the two functions, which would be x squared plus 2 minus negative x dx. Okay. So this is f minus g. And so once you have the integral set up, and that's really probably the most important part of this whole thing is learning how to set these up, the actual integration component to this should be very easy. And so we're going to simplify first. We'll have x squared. This becomes plus x plus 2 dx. So when we integrate, we get x cubed over 3 plus x squared over 2 plus 2x between 0 and 1. So ultimately, it gives us 1/3 plus 1/2 plus 2. Common denominator would be 6. So we're going to have 2/6 plus 3/6 plus 12/6. So we get 17/6 as our area. All areas should always be positive, so the fact that we got a positive answer, that should make you feel good. Just because we got a positive answer doesn't mean it's right, but in this case it is. So that area here is 17/6. Again, very basic question, pretty simple. They do get more difficult from here. So in this case, we're looking at the area between intersecting curves. So that idea of the width is still to be determined. The A to B, those vertical lines that we looked in the last example, 0 and 1, are not given here. So it says find the area of the region bounded by the graphs of f of x, which is x squared minus 5x minus 7, and g of x, which is x minus 12. And so if you were to graph these two functions, this picture clearly defines those. You see the parabola and the line. And the area bounded between them would be this blue area here. Notice this brown area on the side here. This is not the area bounded between them. This is the space between them, but it's not bounded in that there's nothing stopping this from keep going to the left, right? There's no bound there, and there's no bound defined in the problem. So the only thing that's bounded between the two would be this space in here. So we want to find that area. Now the problem is we need to know the width. And the width comes from finding where these two functions intersect, and then following that up to the x-axis and knowing what the width is that we're integrating over. Well, the way you find the intersection points between any two functions is to set them equal to each other. Okay? That's how we're going to find these intersection points. And so in this case, it would be x squared. We'd have to solve this equation that we're going to set up. So it would be, say, x squared minus 5x minus 7 equals x minus 12. This is just a simple quadratic equation, so set it equal to 0. We get x squared minus 6x, add 12, so we're going to get plus 5 equals 0. If we were to factor it, x minus 1, x minus 5 would be your factors, and you would get x equals 1 and x equals 5. So those are the x values for the intersection points here between the two functions, and therefore that's going to be the width on the x-axis. They're x values, that's the width on the x-axis for our interval of integration. Now, as far as which function is on top and which function is on bottom, the bigger minus the smaller, clearly this entire time, if I look at this vertically, the line is on top, the parabola is on bottom. So g is the top function, and f is the bottom function. So if I'm going to set up my area, the integral would go from 1 to 5, that's your width, of x minus 12 minus x squared minus 5x minus 7 dx. So then what I would need to do would be to simplify before I integrate it, distribute this negative in here, maybe collect any like terms we could have. So I have 1 to 5, I would get negative x squared. I'd have, what else would I have? I'd have a positive 5x, or positive 6x, I should say. So that'd be positive 5 and the positive 1x. And I would get a minus 5 dx. So now I integrate. This should be the easy part. The hard part was setting up what would give us the area. Now we need to actually integrate. Pretty easy. X cubed over 3 plus 6x squared over 2 minus 5x between 1 and 5. I would simplify this to be just 3x squared. Okay. So I'm going to plug in 5. I would get negative 125 over 3 plus 75 minus 25. And then if I plug in 1 and have to subtract that, I would get negative 1/3 plus 3 minus 5. Again, that's going to be subtracted, so then all those signs would change. So I would end up with negative 124 over 3. That's these two. And then I would have 50. This is a minus 2. So that would be plus 48. So in the end, I would get 20 over 3. And so that area that we were looking at here is 20 over 3. So this one was a little different than the last one in that we had to find those intersection points so we could calculate our width. And that'll happen sometimes. In the previous example, there was no area bounded by the two functions. You had to bound them on the sides. You had to, you had your parabola, you had your line. In order to bound an area, we had to create sides to this area so that we could get our width and we could have an enclosed space. In this case, we were already enclosed by the two functions, so the width was not needed to be given in the problem, yet calculated by finding the intersection points. Okay, here, this one is a little more general. We would have a lot we have to work out here. So the sine and the cosine curves intersect infinitely many times because of the wave pattern. Bounding regions of equal area because of the symmetry of these waves. Find the area of one of these regions. Since they're all equal, it doesn't matter which one we would find. So you look at, say, like this area here, this area here, they're equal to each other. But also, this one right here is equal as well, even though it's going sort of up from left to right, so down from left to right. I don't know how you would explain that. But all these areas are the same, so it doesn't matter which one we find. So what I'm going to do is I'm going to pick one, and I'm going to pick this first one, and I'm going to find this area in here. So in order to do that, I need to know which function is on top and which function is on bottom. But if you look at the waves, the red wave is the sine wave. The black wave is the cosine wave. Okay, and you can see that just by looking at the intersection points. The red wave intersects the x-axis at 0. This looks like it's roughly around 3, which would be actually pi. And this is a little bigger than 6, which is 2 pi. Okay. And then you see this one, has this maximum point at the y-axis. That tells me it's the cosine. So anyway, you can see which function's on top and which function's on bottom in this space. So we're talking about this space. The sine is the top function. the cosine is the bottom function. And that's consistent the entire time. Eventually we'll talk about what happens when it's not consistent. Okay. So what we need is the width. We need to know what width on the x-axis are we talking about here to integrate over. And so it's all about finding these intersection points here and here. So we need to find where the two functions intersect. Well, those intersection points can be found by setting them equal to each other. So sine x equals cosine x. Okay, cosine x. And so you got to solve this trigonometric equation. Lots of different ways we can do this. One way to do this would be to say, when is the sine and the cosine functions equal to each other? You know, what angle, when I plug it in here and here, do I get the same answer for sine and cosine? And if you notice, that answer has to be in this space here. There's a lot of them. But look, so if we look at where we are, if this is, say, pi right here, this one would be between 0 and pi, and this one right here would be between 0 and 2 pi. And so you could come up with the fact that x would be pi over 4, and x would be 5 pi over 4, if you know your unit circle. Another way we could solve this would be if we divide by cosine. So we would get sine x over cosine x equals 1, because if I divide this by cosine, I would get 1. And then sine over cosine is tangent. And I could ask myself, when is the tangent going to be equal to 1? And again, pi fourths and 5 pi fourths. So there's your width. So pi fourths and 5 pi fourths. So now it's just a matter of integrating and getting your answer, which again should be easy. The integral of sine is minus cosine x. The integral of cosine would be sine x between pi fourths and 5 pi fourths. The value of sine and cosine are the same at each of these values, but what is it? The answer would be square root of 2 over 2 or negative square root of 2 over 2, depending on which one of these we're talking about. So if I plug 5 pi fourths in, I'm going to get negative square root of 2 over 2 for both sine and cosine. If I plug pi fourths in, remember I have to subtract this, I'm going to get positive square root of 2 over 2. Don't worry, don't forget about all the negative business. So these have negatives in front of them already. When I plug it in, I get a negative square root of 2 over 2 for this one. And in the second one, I have to subtract what I get when I plug pi fourths in. So if I keep track of all this, what do I get? These two negatives are positive, these are positive, so I get square root of 2 over 2. I get another square root of 2 over 2, both positive. This negative distributed in here, make those all positive. So I have 4 of these. So I have 4 square root of 2 over 2's. Cancel that. I would get 2 square root of 2 over 2 as my answer. And when I'm looking at answers, I prefer this answer to whatever you would plug into your calculator and give me some decimal answer. This is the exact answer for this area. I love exact answers. Okay? In some instances, the exact answer may not be the best, but in most instances, I think it is. If you give me the calculator decimal answer, even if it was 10 decimal places, it would be rounded at some point. Because this is an irrational number. It can never be described by a finite decimal. And so if you gave me your calculator answer, you'd give me an estimate for the answer. Well, if you learn all the way back in Calc 1, the whole point of doing these integrals is to not do estimates, right? Is to get the exact value of an area. We go from an estimate, we use a limit to help go from an estimate to the actual area, which is the definition of integration in the first place. So I prefer this exact area, the exact answer as my answer for any of these problems. Do not give me the decimal representation that your calculator told you. Do the computation. You should be able to handle it. Now we're going to step it up one more time. We're going to look at curves that intersect at more than 2 points and therefore bound multiple areas. And so here's an example of two functions that intersect 3 times, and they bound 2 areas. And we want to find the sum total of both of those areas combined. And so looking at this picture I have here, you have this red curve, which would be the cube here, that's the f of x, and you have the green the black parabola, which is your g of x. And graphically, you can see they intersect here, here, and here, bounding this area in here, and bounding this area in here. Now, having this graph available to you does make things a heck of a lot easier, but not necessary for us to do the problem. We could simply get this problem done without looking at the graph whatsoever, but one thing we would need would be the intersection points and knowing how many intersection points there are, and that would be found by setting the functions equal to each other. So if we set f of x equal to g of x, we would get 3x cubed minus x squared minus 10x equals negative x squared plus 2x. And this is a cubic equation, so the best way to solve would be to set equal to 0 and factor. So we'll bring these over to this side. I would have 3x cubed. I'd have add x squared, they would cancel, and subtract 2x, I'd have minus 12x equals 0. So if I then factored out a 3x, I would then have x squared minus 4, which would give me x equals 0, and then x equals plus or minus 2 from the x squared minus 4. So I got 3 intersection points. Now, what I would need next would be to know with those intersection points, which clearly this one is negative 2, this one is 0, and this one here is positive 2. I'd have to know which function is the top function and which function is the bottom function, which one's bigger, which one's smaller. So I know how to subtract them. And it's not necessarily going to be consistent in both cases. It might not flip in both cases. We have to decide that. Well, clearly from the picture here, the f is on top and the g function is on bottom. And here, the g function is on top and the f function is on bottom. But if we didn't have that graph available to us, how could we do this? Well, pretty simple. Let's plot our intersection points just on a number line. So here's negative 2, here's 0, here's 2. So these are our widths, right? And so between these widths, we would have to figure out how we're going to calculate the height. So which one is on top and which one's on bottom. Same thing here and same thing here. And so the way we could do that is figure out which one has the bigger y value and which one has the smaller y value. And since these are the only intersection points that we have, that whatever y value in here is the bigger one, it should be consistent across this whole interval. So if I pick a random y value in here, I deleted that. So I pick a random y value in here, let's say negative 1, and I plug it into both g and f. Whichever one gives me the bigger y value would be the one that has the bigger y value this entire interval. And the same thing here, if I plug 1. 1 is between 0 and 2. It's just a number somewhere in between 0 and 2. Whatever function I plug that into that gives me the bigger y value, I would go. So if I looked at, say, f of negative 1 and g of negative 1 and f of 1 and g of 1, and I looked at the value of all those, I could determine which one is on top and which one is on bottom. So that's easy, just evaluating. You plug it into these things and you see. But what you're going to come up with is, in this first one, f would give you the bigger, g would give you the smaller y value, and here it's going to reverse. It doesn't always switch. Sometimes it'll stay, the same one will stay on top. You could have a function that does this, and the other function does this, in which case the top function, even though it's 2 separate areas and 3 intersection points, the top function stays the same. I mean, that's not common, but it could happen. So you should check all this out. But having the graph available to you over here definitely makes that a heck of a lot easier. But again, not necessary. This is what I'm trying to tell you, is that you could use just simple tactics like this to determine how we're setting up our integral. All right, so we have two integrals we have to do. We're going to add them together, and we have to switch the top and bottom functions. So the first integral, actually let me get some space in here so I can work. So the first integral would be the integral from -2 to 0. And we just said f was on top, so 3x cubed minus x squared minus 10x minus the g of x, so -x squared plus 2x dx. And that's going to be added to this other one, which goes from 0 to 2. And we flip them, so then this will be -x squared plus 2x minus 3x cubed minus x squared minus 10x dx. So this negative has to distribute here, this here, collect the terms, see what we get. So we get -2 to 0. We're going to end up with 3x cubed minus 12x dx plus this one will be 0 to 2 of -3x cubed plus 12x dx. And so now you integrate and plug in your limits of integration. So we're going to get, what, 3x to the 4th over 4 minus 12x squared over 2. So let's just go 6x squared. That'll be -2 to 0. And this one would be -3x to the 4th over 4 minus, plus 6x squared between 0 and 2. Plug in your numbers, evaluate, and then you're done. So what would we get here? We'd get 0. We plug in -2, which would then have to be subtracted. So we're going to get, what, 3 times 2 to the 4th is 16 over 4. So 3 times 16 over 4 minus, 24. That'll be plus. This one I plug in 2. I would get -3 times 16 over 4 plus 24. And when I plug in 0, I would get 0, so subtract that out. So a little bit more work here. This negative distributes in here. So you have a negative, positive, positive, and we end up with, so in the end we get 24. And so the combination of this area plus this area would be a sum total of 24. But this one again is different because now we're intersecting multiple times and then bounding multiple areas. And we want to find the sum total. But as long as you do the top function minus the bottom function, even if it switches, then you just create a new integral. You can keep going and you can get your areas. All right, now when we say top and bottom function, what we really should be saying is bigger function and smaller function, because it's top and bottom is relative. It's relative to which way you're looking. Typically what we look at is vertically, right? When you look at vertical rectangles, say in this picture right here, okay, you have functions of x, and functions of x run horizontally. So these two functions of x run horizontally. And your top and bottom function line up vertically, right? But it's really the bigger function and the smaller function is what we're really talking about here. Now, we could also be talking about functions of y. And when we talk about functions of y line up vertically. This would be a function of y, and this would be a function of y. Graphically, that's how you would do them. They go vertically up to down. And so when we place our rectangles in here, we change our orientation and look at them this way. So the top function and the bottom function change orientation in that it's right and left. But it's still bigger and smaller. If they're functions of y, they're measured this way. They're measured across instead of measured this way. So we're measuring them with horizontal rectangles. So the top is the bigger function, and therefore the right function, and the bottom is the left. So we're just changing our orientation, but using the same concept. And then the width is calculated this way along the y-axis because everything has to be related to the same variable. These are functions, let me get rid of all this, you can't see anything here. These are functions of y, which we would then integrate with respect to y over an interval of y. So everything's in terms of y. We just changed our orientation to go this way instead of in this vertical format. You have to have this ability to change your orientation. You shouldn't always have to integrate everything with respect to x. You should be able to change the variable to then talk about integrating with respect to y. The big difference, vertical rectangles put into your picture versus horizontal rectangles put into your picture. And you need to look at the area and say, which way would be the best way to set up this area? Vertically or horizontally? And it will make your life 10 times better when you learn how to do this and learn how to do it easily. Because if you have to force everything into a x integral, where you're integrating with respect to x and you're setting your rectangles up vertically, which you've seen as the most common way you've done it so far, if you're forced to do that all the time, you're going to make things harder on yourself. Having the flexibility to change your orientation and look at things from a different perspective, look at it horizontally versus vertically, you can pick what works best for you in a given problem. And so here's a typical example, a fairly easy example, and we'll spend more time working on this. The next thing we're going to talk about is volume, and we'll get more practice in doing things horizontally, because volume really boils down to talking about an area. And so if you look at this, if we were to graph, say, x equals 3 minus y squared, that would be a parabola, but a horizontally oriented parabola. In this case, the red curve is that parabola. Its vertex is on the x-axis instead of on the y-axis, and it's moved 3 units to the right instead of maybe, say, 3 units up, which you would typically do. And it's flipped over because of the negative here. So all these things you've learned before, just switching the x and y axes around. And then this is just a line, x plus y equals 1, which is this black line here. And so the area in between is clearly in this space in here. Now, we look at this one of two ways. So, one way to do it would be to look at it vertically. Totally fine to do until we get to this point. The red curve is on top, the black line is on bottom, and then once we get to this point here, we have a problem. Because the top of the rectangle and the bottom of the rectangle are hitting the same curve. So the only way to handle this would be, one, to do this in 2 separate areas, so the red area and the blue area, and then add them together. Then we would have to take this parabola and take it and split it into 2 separate curves. The top half of the parabola and the bottom half of the parabola, so that one of them is on top, one of them is on bottom. That's a lot, right? And that's if we were forcing to do this in a vertical format. But we don't have to do that. What if we did it with horizontal rectangles? And our top is the right side and the bottom is the left-hand side. So the bigger with respect to y as our function, and therefore the x is how we measure the height, right? Because think about it, in a function of x, y, when you look at a function of x, y is how you measure the height, right? The y values, because f of x and y are interchangeable. Well, for a function of y, the x's are how you're going to measure the height. Okay, so let's go back. Anyway, if we do it this way, we can have the same top function. Every one of these rectangles I'm drawing here, okay, with just horizontal lines, they're all rectangles though. The top part of the rectangle hits the red curve, and the bottom of that same exact rectangle hits the line. So if we do it horizontally, which is fine, we would just have to make sure we integrate with respect to y. We definitely have a top and a bottom function. This is the top function and this is the bottom. The only problem is we'd have to write these as functions of y. This is already written as a function of y. You know, x equals 3 minus y squared. That's your function of y. We'd have to write the line the same way, which would be x equals 1 minus y. That's easy to do. And so we have our top and our bottom, which is really right and our left functions. And that's how we're going to do our subtraction in here. The width is now calculated this way along the y-axis, which will be based off of these intersection points. And that'll calculate our width along the y-axis in here. So we need to find intersection points, and the way you do that is simply by setting the functions equal to each other. Again, the functions of y equal to each other. So our intersection points would be 3 minus y squared equals 1 minus y. Figure out what y values you would have for these two intersection points. Because again, we want to know the width along the y-axis. Width goes this way, height goes this way. And we would get, say 0 equals y squared minus y minus 2. So factor that, you get y, minus 2, y plus 1. So y equals 2 and y equals negative 1. Okay, so there's your width. Here's the subtraction. So let's set up the integral. Remember, everything's got to be in terms of y. So the width is in terms of y, negative 1 to 2. The functions are in terms of y, 3 minus y squared, minus 1 minus y. And we're integrating with respect to y. All that has to match up. If you don't do that, you're going to get the wrong answer. All right. So we did it horizontally. Everything's in terms of the y variable. And now it's time to integrate. So once it's set up, it's easy. So we got negative 1 to 2. We got minus y squared, plus y, plus, try one more time, plus y, what was it, minus 2? Or plus 2, plus 2, okay, and dy. And so we get negative y cubed over 3 plus y squared over 2 plus 2y between negative 1 and 2. Just plug all these numbers in, do your basic computation. So negative 8/3 plus 4/2 plus 4. Subtract out what happens when you plug in negative 1. So that's going to be what? Positive 1/3 plus 1/2 minus 2. Do your quick computation. You end up with, I come up with 31/3. I think that's right. I did quick computations. Let me double check that real quick. I'm going to have minus 8/3 is a minus 1/3. So that's minus what? That's minus 9/3. Then I'm going to have 2, 4, 6. And if I distribute this in here, it's going to be another 2, so that's 8, and minus 1/2. So common denominator would be 6. All right, so this is already wrong. So common denominator would be 6. So I'm going to have what? Negative 18 plus 48, minus 3. So that's going to give me 27/6, and 27/6 simplifies to 9/2. So yeah, I was wrong. 9/2. It helps to write it all down. All right, so 9/2, that's the area here. But the whole point of this problem is the horizontal orientation that we're looking at. Make your life easier. Don't stick to vertical orientation all the time. Sometimes it's better to look at it in a horizontal fashion. And you just switch your variables up and look at everything in terms of y.